on the registration fee.
Absolutely. So when we initially saw the prompt, it was obvious that there were a myriad of different paths we could take. And I'm going to pass it off to Jack to talk about some of the initial questions we had when looking into this question.
Initially, we were very interested in the situation part of prompt number 1. And basing off of that, we wanted to use a regression to predict the probability of a successful passing play call given a certain situation. And initially, we were using a very small data set, not giving a lot of context to our model, and therefore we weren't getting anything better than a blind guess. And so therefore we took that and we reassessed our method and we said, okay, how much context do we need in order to properly define a situation? And then also we looked at what is optimal? What are we trying to achieve? What is it a path, like, what are we looking for there?
Right.
And then how can we model that given the zone that was asked for in the competition prompt and as well as by situation? So first we looked at by yard line. How is passing rate affected by yard line across these zones? From zones 2 to 5, we see a pretty constant rate, barring the 1 yard line. But in zone 1, we see a drastic difference coming from your own 1 yard line going into the 25. And so how can we get more context for that? So we then go on to passing rate by down, and we can see down has a major effect on the passing rate. So you can see first down teams are less likely to pass than on third down. So that was logical to include that.
Yes.
But we didn't want to be too simplistic as we ran into with our regression model. And so therefore we said, why don't we go and look at NFL faster data, and we can get win probability to define some context. Looking at win probability using NFL passing rates from 2014 through 2020, which was the range of our data set, we can see NFL teams would pass at a much higher rate regardless of the zone on the field, given a certain win probability situation. And we just defined some categories for win probability. We say lost is a win probability of less than 10%. And this really helps us give us a better understanding of the passing rates by the zone. So finally, we decided on these variables to define our situation. Down and distance, as we saw before, win probability as well, grouped by those categories you saw. Field zone as defined by the competition, and time left is one we took from real NFL context. We read a little bit of Bill Walsh's book, and he defined some situations such as 1 minute left, 2 minute left, 4 minutes left in a half or a game, and regular time remaining would be another one. So using this, we figured we might be able to simulate an NFL game or an NFL drive. And in order to provide more context on how we did there, I'm going to pass it off to Steven.
Right. So we felt like we need a simulation because we wanted a controlled environment in which we could affect or change only the pass rate. We wanted to see how that would affect how a team performed on a drive level. Now, one of the reasons this is important is it actually gives us insight into actual NFL play calling logic, because we're kind of borrowing their play calls in a sense.
Right.
Given the situation that we're in, we look at what they've done in the past. We also weight it based on how successful those attempts were. That's what drives our decision-making logic. So the simulation is fully aware of the situation before it calls a play. We pass that information to it. Before it calls anything, it asks the following question: what is the expected value of a designated stat? For our purposes, we used EPA or WPA, win probability added. What is the expected value of that stat given the situation that we're in and given that the play call is a pass? It compares that exact same parameters to the expected value given that the play call is a run. And the initial method we used was a deterministic method. Even if the pass value was only marginally better than the run value, it would pass 100% of the time. That was our kind of naive first pass at a play calling logic method, but we got a little more complicated as we continued through it. The key metric we identified to actually gauge how our play calling logic was doing was cumulative drive EPA. This is EPA on a drive level rather than a play level. We actually wanted to make sure that we were doing something that was creating longer sustained drives rather than just potentially more explosive plays at the play level. So we posit that if our play calling logic through the simulation is able to produce a higher average cumulative drive EPA than the actual NFL average, and the only thing we're changing is the pass rate, then the pass rate that we're feeding into the simulation must be better than the average league pass rate.
So I'm going to take a moment to walk through some of the step-by-step processes that our simulation used. So big picture context, we're trying to simulate a drive in an NFL game. And so this drive will start randomly with either a punt or a kickoff play, which Stephen and Jack will talk about in a little bit more. And then at the beginning of every play in that drive, we analyze what situation we're in using the variables that Jack mentioned earlier, such as down, win probability, and the other things that we mentioned. Once the simulation knows what situation it's in, it will subset all of the play-by-play data from 2014 to 2020 that we have into only data that applies to those situations. Once we have that subset of data, we then divide that pool into times when a team called a run play versus times when a team called a pass play. And then we looked at a statistic of interest from each of those sets. That was usually EPA or WPA of a given play. What we then did is we ran Bayesian bootstrapping on those two subsets for a statistic of interest. For example, we would take the EPA of the rush subset, the EPA of the pass subset, and then compare the two in order to choose a binary variable. Do we call a rush play or a pass play? We use 3 different methods to make that decision, which we'll talk about in a little bit. Then, once we made that binary decision, whether to rush or pass, we chose a random play call within that subset of data. So if we choose to run, we would then choose a random run play, regardless of what the EPA is. And this is a point that I'd like to emphasize. So our simulation didn't add any play calling intelligence on top of adjusting that binary variable of whether to rush or pass, which allows us to see if our simulation performs better than the NFL play-by-play data season-wide that we have. We can then infer that our play rate, our pass rate rather, is better than the current data. So we're now going to talk about the 3 different methods that we use, but first I'm going to pass it off to Stephen, and he's going to talk about the control sample that we compared our methods to.
What you're seeing right now is our method 1, but if you actually look in the blue on that chart, that's our control group. The control group is the base simulation with no play calling logic at all. It calls a play completely random based on the situation it's in. In the long run, this will model actual average NFL play calling logic. We compared the control group to the provided data set, and we found them to be statistically similar, thus telling us that our control group and our simulation was well calibrated to actual NFL results.
Absolutely. So once we had a control set of data, we then ran the simulation for 1,000 drives for each method. There are 3 methods, and we'll walk through those one at a time. So remember that we're drawing from a Bayesian bootstrap sample of rush statistics of interest and pass statistics of interest. So for method 1, we used WPA of a play as our statistic of interest. And we simply took a naive average of the rush WPA given a certain situation and the pass WPA given a certain situation, and then use that to choose a random run or a pass play. We see that only changing that binary variable still produced a statistically significantly better cumulative drive EPA than the play call data from actual NFL seasons. You can see on the right, the t-test result is statistically significant. However, I'm not going to dwell too long on method 1 because there are better things to come. Method 2 ran a similar technique as method 1. However, it took into account EPA as the statistic of interest. So it took the average bootstrapped EPA of rush versus the average bootstrapped EPA of pass. You use that to make a play call decision. Similarly, got statistically significant results.
I want to interject real quick. Both method 1 and 2 use the deterministic play calling model that I talked about earlier. Even if the pass is marginally better than the run, it's going to call pass every time. That's what we decided to change for method 3, and we found good results.
Absolutely. So for method 3, both of the previous two were simply comparing means. So even though that's effective in some way, it didn't really take advantage of the variance and the insight that the Bayesian bootstrapping technique could fully allow. So for method 3, once we had a Bayesian bootstrap sample of rush WPA, or EPA rather, for method 3 we used EPA, a Bayesian bootstrap sample of rush EPA versus pass EPA. We then drew a random sample from those two distributions, compared those in order to make our determination of whether to rush or pass in a certain game. And across the 1,000 simulation runs that we did, this takes into account things like variability that the previous two methods couldn't. And we see on the right that it has by far the most statistically significant p-value, showing that our simulation was indeed able to outperform the average NFL team, only adjusting pass rate. Steven's going to say a couple words about the conclusion.
Yeah, we found method 3 to produce the highest gain in cumulative drive EPA compared to our other methods. This is important because the main change in method 3 was we added an element of randomness. The model actually made a decision based on the probability that the pass would be better, not based on the deterministic value. This may show that an element of randomness does produce effective results in the NFL when you're talking about play calling.
Yep.
All right, I'm going to tell you guys a little bit of insight on how the simulation works. So it drops us in on a random play. This is any drive start play. It can be an interception, a fumble, kickoff, punt. It's a play where a drive started and we are now the possession team. We now inherit all the data from that game, from how much time is left in the game to what kind of roof does the stadium have. That is now the exact situation that we're in and that will remain in for the remainder of this drive. From there, it assesses the historical EPA data like we just talked about based on the situation we're in, makes a pass or run call, and then picks a random play from either the passes or runs depending on the decision it made. We then reassess our situation, call another play. This process continues until the drive ends, either via fourth down, safety, interception, or fumble, or of course, a touchdown.
As you can imagine, as Steven just said, there are some situations where we're filtering and we're getting way too specific. And so what can happen in the simulation is we attempt a situation that has actually never happened in an NFL game,
Right,
given our domain of 2014 to 2020. So in that case, the filtering will, in effect, zoom out. And the first thing it zooms out on is our zone on the field. So we categorize zones 1 through 5. If we're in zone 4, we'll then say, okay, you can still call plays from zone 3. And that was our way of mitigating that issue. And therefore, we can still produce a play call given that situation. The other thing we run into with the simulation, and this is probably the most major drawback, is there's no publicly available play-by-play context, at least that we could find, that defines any defensive adjustments. I think we all three agree that fundamentally, determining a pass over a run rate would be most majorly affected by how the defense is lining up. You probably wouldn't want to run the ball versus a very heavy box. And we don't have that context in the data. And so we weren't able to use that, but we still produced a simulation given what we had.
Before jumping into the results, which are the direct answer to the prompt, I'd like to revisit the big picture of our method. So we decided to simulate NFL drives because we believe that was the best way to get an overarching context to everything. We then, in the previous slide, showed that these simulated drives, only by adjusting pass rate, were able to outperform actual NFL play-by-play data when evaluating it based upon cumulative EPA in a drive. So now that we've shown that our simulation does significantly better, we want to look under the hood and see what the pass rate per zone was in each of our simulated runs. And that's what we're going to see now. So this graph is the first one you've seen so far that is a direct answer to the prompt that was given to us. So we see this mirrors the graph that Jack explained earlier, breaking the field down by zones, zone 1 being as far from a touchdown as possible, zone 5 being the red zone. And the black line you see is the current NFL pass rate, given our data from 2014 to 2020. And the purple is the pass rate of the simulated data that we ran for method 3. So as we can see here, even in zone 2, when the current NFL is the highest pass rate, it almost never exceeds 0.75 of a pass rate, whereas our simulation would prescribe pass rates even above 90% in the open field before field goal range. This shows a little bit more of the quantitative view of the graph that you just saw. So these are the optimal pass rates by zone that our simulation would prescribe for the average NFL team. We see that the pass rate is incredibly high in zone 2, which is once again out of deep in your own territory, but before field goal range. And then we see that as you get closer to your own end zone or closer to a touchdown, that pass rate can go down, but it's still substantially above what NFL teams are actually running in a season. So the previous two graphs that you saw related pass rate to different zones of the field, which is a direct answer to the prompt that we were given. But something that Jack mentioned earlier was we found win probability to be a very interesting thing to look at as well when determining pass rate. And specifically, we found that NFL teams, regardless of zone on the field, are much more likely to pass if they are down in a game and much less likely to pass if they are up in a game. And what you're seeing on the screen now is the results from our simulation relating pass rate to zone on the field and to win probability. And as opposed to the data that the NFL play-by-play historic data suggests, our simulation suggests that there may be an interaction effect between win probability and zone on the field, that it should not be a simple decision based upon win probability to decide whether or not to run or pass the ball, even though data suggests that's a primary factor in the NFL's current decision making. I'm going to now pass it off to Jack and Stephen, and they're going to talk about a couple of case studies specific to the 2020 season.
So if we take these results that we've just presented, that we have the optimal passing rate, and we already filter for situation. If we get more specific and use the PFF grades that we were provided, and we filter on those, we filter to provide our play set with only plays called by teams with similar capabilities. If we take pass grade to be a measure of a team's capability in the passing game, we filter on those, and we filter around teams that are similar to teams that we choose are interesting to us. This will give us insight into how often this team should have passed in order to achieve a higher cumulative drive EPA than they got for the 2020 season. The first team we took a look at for this study was the Cleveland Browns. Our motivation, first and foremost, was a run-heavy offense. As we've seen, we prescribe ridiculously high passing rates, and so looking at something that contrasts that would be particularly interesting. Cleveland's rushing rate is 4th in the NFL, and they're a particularly average play action offense, and we'll get into that in the third part of the prompt. Also, we have Baker Mayfield as an alumni from the University of Oklahoma, so we're very proud of that.
Boomer Sooner.
And also, so taking a look at this, we can get a simulation of how often they should have passed given the 2020 season. And here we go. We look at Cleveland's 2020 cumulative drive EPA in blue, and we look at what we simulate on teams that are very similar throughout the 2014 to 2020 based on PFF passing grades. And we use those plays, and we say we can produce a marginally higher cumulative drive EPA. We see we're producing less drives that are negative in cumulative EPA, and we're producing more steady drives, as we can see at we're producing a drive EPA around 3, which is highest above 0, the highest density above 0. So although we don't produce a statistically significant mean difference, we still think it is significant that we are producing steadier drives as observed by the density plot. Finally, we take another look at that graph that groups by yard line, and we see our overall method 3 in blue, which is the ridiculously high passing rates. But we also see what we observed from Cleveland in 2020, which is the gray and black line. For purple, that's what we prescribe to Cleveland to fix their passing rates. And we can see we should increase them in zone 1. In zone 2, we get a significant increase, but look at zone 5 of particular interest. Zone 5, we actually say Cleveland called nearly optimal passing rates given their talent and given the context of their passing and rushing, receiving, all these PFF grades. And we believe that's significant because we can draw a conclusion that Cleveland called near optimal passing rates in the red zone. And on the right, we can see those broken down by their average passing rate by zone.
The second team we looked at were the Arizona Cardinals. In contrast to Cleveland, they actually have a slightly below average passing offense. They do have a play action heavy offense, but you can see their run block grade is far and away the weak spot of the team here. What makes the Cardinals such a unique offensive makeup is that a lot of their success on the ground is actually bolstered from the quarterback position. Kyler Murray is an explosive runner, the likes of which we haven't really seen a lot at quarterback in the NFL. That makes the Cardinals kind of a unique team to prescribe a pass rate to. So we were interested to see how our simulation would deal with them.
And Kyler Murray's from OU, Boomer
Yes.
Sooner.
So here you see the results of our simulated Cardinals drives. In blue is the actual Cardinals 2020 season cumulative drive EPA. In red is our simulation of it. So you see a little bit less of a difference compared to the Browns. Maybe this is to be expected. The Browns have a more efficient passing offense. They're able to gain more from passing it more. And another thing we notice here, like Jack mentioned with the last data set, we're producing significantly more drives of just above 0 cumulative EPA. We're getting, even if they're not scoring drives, we're getting positive drives and flipping the field more often. We're getting backed up less often. You can see the density on the left side of 0 much lower in the simulated data set. So now we're going to move on to the yard line chart for the Cardinals. As you can see, the Browns were a little bit lower than the Cardinals in this one. The Cardinals here represented in purple. Gray is the Cardinals' actual pass rate in 2020. Purple being our simulations version of it. And then, blue
right.
is actually the method 3 prescribed pass rate for the average team.
Right.
So you can see our model actually suggested the Cardinals pass it a little bit less than the average team. We just saw they have a slightly below average pass EPA. They have a unique and threatening run attack that makes them a good candidate to run the ball more often.
Finally, the last part of our prompt asked us to look at the play action scenarios of the 2 case studies.
So going back to the Browns, if we remember, they were a very average play action rate team, and this is in alignment with that. So we can see play action rates for all NFL teams basically go down in zone 4. In fact, Cleveland used a lower rate in zone 4. Particularly interesting is zone 5, where they are performing above the NFL average. And zone 5 is near the goal line. Zone 5 is from the 10-yard line into the goal line. And we believe that this was Kevin Stefanski's way of using his highly graded NFL rushing attack in order to use the defense's expectation of a run play in that zone of the field against them.
Mm-hmm.
And so there's strategic elements based on how your team is doing in PFF grades.
We also looked at play action rates for the Cardinals, and as you can see, we talked earlier, they're the 6th highest play action team in the NFL. The bulk of that play action actually comes when they're in their own territory or just outside of it. The biggest difference far and away is in zone 1, which is from your own goal line to your own 25. It seems that Cliff Kingsbury is well aware of defense's ability to key in on the run when an offense is backed up in their own territory. Teams like to favor the run in those situations. You don't want to get a safety or something like that. That's where Cliff likes to pull the play action, try to get the safeties to bite, maybe get something open downfield.
Thank you all so much to everyone who listened to our presentation. Thank you, judges, for volunteering your time. And a big thanks to the competition hosts. We had a blast putting this presentation together. My clock says we have about 6 minutes left, and we would welcome any questions that you have about our presentation.
Great work. I guess my question is, was there anyone that went above those astronomical pass rates as far as, like where would Kansas City be on that, or Buffalo? I'd be curious to just, kind of see how many teams actually went above that blue line.
Unfortunately, we didn't break down every team. So yes, you're absolutely correct. If we had gone through and actually chosen Kansas City, we probably could have observed an answer to your question. However, in the prompt, we had to choose 2, and we chose the Browns and the Cardinals. But yes, you're absolutely right. That would be particularly interesting.
I will say that part of our decision making, it takes win probability heavily into account. A team like the Browns was ahead more often, and that's also part of the reason that we prescribed a higher run rate. there's definitely a chance that it would prescribe a higher run rate for a team like the Chiefs, who have a lead for a lot of the games that they're in.
Mm-hmm.
Hey, sorry. So when you're talking about like win probability with the lead or a deficit or whatever, like how did the simulation is pulling from other situations where a team had the same win probability at that, like, is that what it's like taking a set of plays that occurred when a team was ahead or behind by that amount?
Yes.
It's based on win probability. We grouped
Right,
it. We split into 7 groups for win probability. So if it's within that group, any plays within that group are eligible to be called.
Got it. But you weren't like simulating how much time was coming off the clock and then remodeling the win probability, were you? Or were you? You were. Got you. So yeah, I got you. Thank you.
Yep.
What would you say is the single biggest limitation? Like if you were to present this to, how confident would you be going to a head coach in the NFL today and presenting your recommendations by game situation? And then if like, what would you say is the biggest limitation on your confidence?
I'm particularly worried about the lack of context into the defensive adjustments. We looked into trying to implement a model that says if you pass successively on a drive, how much less likely are you to get a successful pass? And we tried to do a linear regression and relate that pretty simplistically. And we wanted to implement it, but it wouldn't line up properly.
Right.
And so that was our attempt at providing context. But again, with not having publicly available context as to how many players are in the box, where the safeties are, anything like that, we don't think that we're not confident in that aspect of our simulation.
Yeah, if I could answer that as well, we weren't able to find any real evidence for statistically significant evidence for there being a lower expected EPA when your pass rate goes up. There is if you just look at base data, but when filtering for win probability, so taking out blowout games, we didn't find any evidence for that. Now, that's hard to apply to our data because obviously we're prescribing as high as a 95% pass rate in a zone. NFL teams don't pass at those rates. We're not entirely sure what kind of effect that would have. To more accurately answer your question, I would have a great deal of skepticism for any model that doesn't include how the defense is going to adjust to you. We did what we could given what we had. If we had data on defensive alignments, we would have gladly included that. It's not in the model, and we want to make that clear, but we still think it's making proper decisions based on the information it has.
Yes.
You mentioned like a hurry up or a 1 minute or 2 minute offense as opposed to kind of the traditional 4 minute, burn the clock offense. Was that baked into win probability in terms of keeping the ball out of the opponent's, hands? Let's say it's a 4 minute situation. Were you factoring in you want to reduce clock and that it's not just optimizing your drive and scoring, but also, wasting time so there's less time left coming back?
Yeah, so our method 2, which looked at WPA rather than EPA, we did see some of that where there are situations where increasing your drive's EPA or your expected points in a drive aren't necessarily the best thing for you to win the game at that given time. So we did find factoring win probability rather than EPA, it can sometimes make more effective decisions in specific situations.
I think we have time for one more question if anyone is interested. If not, then thank you all so much for the opportunity to give this presentation. I'll reemphasize again that we all had a blast making this presentation, and we're sorry that Paxton couldn't make it, but thank you all so much for your time.
Yeah.
Great work. Thank you, guys.
Yeah, thank you guys.